My name is Reinhard Genzel. I'm an astrophysicist, an experimental astrophysicist. I work at the Max Planck Institute, Max Planck Institute for Extraterrestrial Physics. And I'm interested in, my team and I are interested in studying massive black holes and the formation and evolution of the universe.
So first of all, the center of our galaxy is a testing ground for gravity. How did you come to this idea?
Well, it's a longer story. I mean, the general relativity, as you know, was invented, so to speak, as an improvement over Newton's theory by Albert Einstein about 100 years ago. Then it took 50 years until the quasars were discovered. The quasars are very bright, but very, very distant phenomena, which we now know are, with great likelihood, very, very massive black holes between millions to billions of solar masses, which attract, accrete material and are very bright. And this idea that you would have these supermassive black holes is one of the things which the theory of Einstein predicts. But the question is it true? And so the quasars are much too far away at this point to make detailed measurements and test whether they are really truly black holes. So that's where the galactic center comes in. The galactic center is 24,000 light years away. That's really very close. And so over this last 3 decades, we've been able to make measurements with ever better precision, mostly of stars orbiting the very center, showing that there is indeed a mass, a compact mass there, about 4 million solar masses. And the evidence has gotten better and better and better that this is indeed an Einsteinian, if you like, or a Kerr black hole.
The effect that Einstein's general relativity theory predicted is the Trostle precession. What is it? Can you explain this to me?
Well, if you envision the solar system and what Newton and Kepler knew about it, then you have the planets orbiting the sun on elliptical or circular orbits. And these ellipses, if there's nothing else in the way of a planet around the sun, is a figure which is always the same. Okay, it stays the same in the orbit, and the planet orbits around the sun for all times. Not so in general relativity. And there are several effects here. One is just due to the fact that the space-time which the sun generates makes the orbit of the planet precess, move forward, rotate, if you like, a little bit forward over time. And the second thing, if the planet, if the sun has an angular momentum, so it rotates, then there's a second effect, which is also a precession. So it's the biggest effect of these two is the precession due to the mass. So in the case of the sun, the precession of a planet was actually detected before general relativity was known. That's not very well known, that the Mercury, the innermost planet, was looked at in the 19th century by astronomers, mainly to look for disturbances on its orbit by other planets. And in this way, Uranus was discovered, actually. And many people at the time thought there might be a planet inside of Mercury called Vulcan. And they were sort of looking for an effect which could not be explained by the other planets. And indeed, they found some, but not Vulcan. They had in fact detected 30, 40 years before Einstein the Schwarzschild precession. And so when Einstein then wrote it down, everyone said, hey, okay, there it is, okay.
So if we already knew about Mercury, why do we need to look at the black hole in the middle of our own galaxy?
Yes, so why are we testing general relativity? Well, because that's the nature of physics. Theories and the famous theory of Einstein is no different here, are only transitory truths, if you like. In fact, we believe there is good reason that the Einstein's theory must be wrong on small scales, for instance, very small scales, where you would have quantum effects and atomic effects and so forth. Plus, there are other theories which are similar to, but not the same as general relativity, which predict slightly different things. So we must, as scientists, that's the scientific method, keep on testing in different parts of parameter space whether a theory is correct in order to either, find it is correct or it is not correct. So that's what we're doing here. We're looking in part of a parameter space in mass, which has not been looked at. I mean, the laboratory experiments or the solar system tests are on very small scales, very small masses. Then LIGO looked at and tested general relativity with so-called stellar black holes, a few tens of solar masses. Here we're looking at an object which has millions of solar masses. So that's very different, and so that's one way we want to test the theory. There's a second motivation we have, and that is to actually show that the object which is in the center of the Milky Way is a massive black hole. It plausibly is so far, but it might not. It might be a double object. It might be a triple object. Who knows? And so by making the measurements we are measuring or have been making, we are basically firming up the evidence ever more that this is indeed a supermassive black hole. Now the third, if you like, is the biology of black holes and their environment, because black holes are not lonely objects. Because of their gravity, they are attracting other objects. One would expect, in fact, to be a massive black hole in the center of a galaxy to be tightly surrounded by a cluster of stars and maybe stellar black holes, or maybe so-called intermediate mass black holes. So these would be objects of, say, a few hundred to a few thousand solar masses. They have not been seen, but they might exist. Our method, in fact, has been able to test that. And to our surprise, if you like, we have not seen anything. The object in the galactic center is pretty lonely. In its vicinity, there is the star, which we've been using, but so far we have not seen anything inside.
Your team has worked on this project for almost 30 years, or around 30 years, which is a really long time. A lot has happened in those last 3 decades. Which are the technological advancements that have happened since?
Yes, indeed. I can see I'm getting older and older here. And I started this when I was in my 20s. And over this time, over this period of time, we have made, measurement improvements of factors between a few thousand to a million in resolution, in sensitivity, etc. The most recent step we took is to replace a single telescope, which one usually uses to make images, by 4 telescopes, which we combine. That's called interferometry. So we take 4 8-meter class telescopes of the European Southern Observatory, the very large telescope in Chile, and combine it optically to an equivalent 130-meter telescope. And the bigger the telescope, the better the resolution. So with this interferometer called gravity, we can measure basically a few centimeters on the moon, if you like, and that gives us the precision to really, nail the motion of a star around a black hole so well that we can see these effects of general relativity.
With gravity, you could show in 2018 another effect of the general relativity. What is that, and why do we need to prove it all over and over again?
Right. Well, the effect we're seeing now is basically true for objects with a mass. Now, general relativity, in contrast to Newton, also says that gravity affects the motion of massless things like light. So if you have a flashlight or a laser and you're close to a black hole and you shine that to us at a large distance, then the laser light has to climb out of the massive gravity around the black hole, and it gets less, its energy lessens, and so we see it red-shifted. So that's one of the effects. The effect we are seeing now is a second effect, but there are many more. The next one we would like to see is the effect of the spin. So if a black hole is rotating, then it takes the space-time around with it, and a star which would be moving there, or gas which would be moving there, would see that and start to wobble. And if you can see that, you can measure the spin of the black hole. Now, these are very subtle effects, very difficult to measure. So you have to slowly learn to climb the ladder of 7,000-meter mountains, then you go to 8,000-meter mountains, and then finally you hopefully end up at Mount Everest.
It's an amazing project. Congratulations on it. What's next? What's the next project that you and your team are working on?
Well, we are in the process of improving the gravity instruments still more, maybe as much as a factor of 100. We'll see. With that, we want to look at distant black holes. So far, we've been looking at the closest massive black hole, but quasars, very, very distant from us, with gravity, we can see the motion of gas and resolve the sizes of these regions and thereby measure then the mass precisely. So if you can do this for many, many quasars, many distant objects, then you can solve perhaps the riddle how massive black holes played a role in the evolution of galaxies. We now know that basically every galaxy has at its center a massive black hole of different masses. We'd like to understand that in detail. There is, if you like, a symbiosis between these black holes and galaxies, and we need to understand that in order to understand the evolution of the universe. So what we see here is the elliptical orbit of the star we've been looking at. It moves around the black hole, which is located in this still on the lower right. You may see this black spot there. It does so in 16 years. For most of this orbital motion, Newton's theory is just fine. It's only when the star enters within a year the region around the black hole here, where it comes as close as about 2 or 3 times the orbital radius of Neptune, when general relativity plays a role. And then what happens is that this ellipse, which is stationary in Newton's theory, all of a sudden starts to shift. It precesses forward by a small amount, but ever more. And basically we have been able to precisely measure this precession and shown that it is identical to what general relativity would predict. Now, as I said, this has several aspects to it. One is the testing of the theory, and the other one is that if there were a deviation from the massive black hole, if it were 2 black holes, this wouldn't look like that. If there were a big black hole and an intermediate mass black hole, it wouldn't look like that. And so by seeing the effect so pure, you can say a lot about the environment of the big black hole.
Perfect. It's super, super interesting. Thank you very much for the time you've given me. And good luck to you and a lot of success for the next project.
Okay, thank you.